Tonight, let's explore that brilliant disk hanging in our sky. Most people take it completely for granted. You wake up, feel its warmth, maybe complain it's too bright. What if that familiar glowing circle actually represents something extraordinary? Picture a cosmic power plant operating for 4.6 billion years, never running out of fuel, never fluctuating enough to freeze or fry our planet. This isn't just any ordinary star. Our neighborhood furnace performs a gravitational balancing act with incredible precision. Shifting our orbit by just a few million kilometers would spell disaster. Earth would transform into either a lifeless ice ball or a sterile desert. Here's something that might surprise you. The sun destroys 4 million tons of itself every single second. It does this just to keep your morning coffee warm. We'll trace this incredible process together, plus discover why living exactly 150 million kilometers from a nuclear reactor might be the most fortunate cosmic accident in the universe. So settle in. Before we begin, leave a quick note in the comments, where you're listening from, or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe. Only if you enjoy these late-night journeys. Now let's begin. Ancient civilizations tracked the sun's predictable path across their skies. They built entire calendars around its reliable behavior. Nobody questioned why Earth seemed to occupy such a comfortable cosmic address. This assumption of natural order would persist for millennia. Then astronomers began mapping planetary orbits with mathematical precision. Their discovery should have terrified our entire species. We don't inhabit some randomly safe location at all. Instead, we occupy a razor-thin zone of cosmic real estate. One small orbital shift would transform Earth completely, move us into a hellish furnace or a frozen graveyard. Our planet sits exactly 150 million kilometers from the Sun. This distance is calibrated with stunning precision. Moving just 10 million kilometers closer would trigger catastrophe. A runaway greenhouse effect would begin. Our oceans would boil away forever, shift us 15 million kilometers farther out. Earth becomes a permanent ice world. Even carbon dioxide would freeze solid. This isn't theoretical speculation. Venus demonstrates what happens when planets sit too close, just 40 million kilometers closer to our Sun than Earth. Surface temperatures reach 460 degrees Celsius, hot enough to melt lead instantly. The planet's clouds contain concentrated sulfuric acid. This acid would dissolve human flesh in seconds. Meanwhile, Mars shows us the fate of distant worlds. Despite having days almost identical to Earth's, Mars became frozen. Water exists only as ice buried beneath the surface. Both neighboring worlds serve as cosmic warnings. They show what happens when you miss the habitable sweet spot. Here's what makes our orbital position even more extraordinary. We maintain this perfect distance while hurtling through space. Earth travels at 107,000 kilometers per hour around the Sun. That's faster than any human vehicle has ever moved. Yet we never drift too close to get scorched. We never drift too far to freeze. Our planet has executed this high-speed cosmic dance for over 4 billion years. Clockwork precision every single orbit. The Sun delivers energy to Earth at exactly 1,360 watts per square meter, just enough to power weather patterns and ocean currents, just enough for photosynthesis, not so much that our atmosphere boils away into space. This cosmic thermostat has remained stable for billions of years. Among thousands of discovered exoplanets, Earth remains unique, the only confirmed world to achieve this perfect solar relationship. What if you could cram 1.3 million Earths inside a hollow sphere? That gives you a glimpse of our sun's mind-bending enormity. The sun stretches 1.4 million kilometers across space. This makes our entire planet look like a grain of sand next to a basketball. Yet this cosmic giant maintains precise energy output. It warms Earth's surface without incinerating every living thing. Ancient astronomers had no way to measure the sun's true size. They could only guess at distance and dimensions. When scientists finally calculated these measurements precisely, the results challenge human comprehension. Light itself takes over 4 seconds to race from one side to the other. At highway speeds, driving across the sun's diameter would require 1,600 years. The sun's surface area exceeds Earth's by a factor of 12,000. You could tile the sun's entire surface with perfect copies of our planet. You'd still have room left over. But here's where the sun's immense size becomes truly mind-boggling. Despite containing enough material to create 333,000 Earths, our star averages only 1.4 times the density of water. This reveals the sun's shocking true nature, a massive ball of superheated gas and plasma. Held together entirely by its own crushing gravity, the sun contains no solid surface at all. Descend through its blazing atmosphere, and you'd sink through increasingly dense layers. Hot gas surrounds you everywhere. Eventually, pressure becomes so intense that hydrogen atoms begin fusing. This releases the nuclear energy that has powered our solar system, powered it for billions of years. Every second, the sun's colossal mass enables incredible conditions. Core pressures 250 billion times greater than Earth's atmosphere. Temperatures reach 15 million degrees Celsius. Only a star this massive can sustain such crushing conditions. It forces hydrogen nuclei together against their electrical repulsion. The sun overcomes this resistance through pure gravitational brutality. The sun burns through 600 million tons of hydrogen fuel every second. Yet it possesses enough nuclear ammunition for another 5 billion years. This stellar inferno will continue burning long after human civilization ends. What makes this scale truly staggering? Our sun represents just an average-sized star. Among 200 billion residents of our galaxy, it's completely ordinary. This ordinary cosmic giant generates enough energy every second to supply the entire United States with electricity for 9 million years. Step outside and toss a ball into the air. Gravity pulls it back down because Earth claims ownership. Now imagine a gravitational field reaching across 6 billion kilometers, controlling distant Pluto's orbital path from that distance. That's the sun's cosmic influence in action. Our neighborhood star doesn't just provide light and heat. It serves as the solar system's absolute gravitational dictator. The sun weighs 333,000 times more than Earth. That's roughly 2 octillion kilograms of concentrated matter. This number contains 27 zeros when written out completely. This represents an overwhelming mass advantage. The sun claims 99.86% of everything in our solar system. All 8 planets combined contribute only 0.14% of the total mass budget. We're basically cosmic dust particles, tiny specks orbiting around a stellar giant. This gravitational monopoly creates fascinating cosmic mechanics. Jupiter weighs more than all other planets combined. Yet the sun outweighs Jupiter by over 1,000 to 1. Earth's entire mass represents just about 0.03% of the sun's total weight. Our planet is so gravitationally insignificant that removing it would cause 0 detectable change. No other planetary orbit would shift. The sun's gravitational reach extends far beyond visible planets. The Oort cloud contains trillions of icy comets. These objects scatter up to 100,000 times Earth's distance from the sun. They still remain gravitationally bound to our star. Some comets take millions of years to complete one journey, yet they never escape the Sun's distant grip entirely. Here's what makes the Sun's mass dominance particularly remarkable. Despite containing 99.86% of solar system material, the Sun rotates surprisingly slowly. It takes 25 days to complete one full rotation at its equator. This leisurely spin seems paradoxical for such a massive object. The explanation lies in how our solar system originally formed. When the proto-solar system collapsed from a spinning gas cloud, most angular momentum transferred to orbiting planets. The Sun traded rapid rotation for gravitational control. This cosmic trade-off allows stable planetary orbits across billions of years. Meanwhile, nuclear fuel burns at a steady, life-supporting rate. Our Sun deserves some honest cosmic perspective. Among 200 billion stars in our galactic neighborhood, our Sun ranks as remarkably ordinary. Not special, not unique, not even particularly noteworthy. Our life-giving star represents the galactic equivalent of suburban middle management. It's surrounded by stellar residents far more spectacular, far more dramatic. Our local furnace barely makes anyone's cosmic highlight reel. Astronomers discovered this humbling truth in the early 20th century. They began classifying stellar types systematically. Our Sun falls into something called G-type main sequence. That's scientific terminology for average yellow star. It burns fuel at a steady, predictable rate. About 7% of galaxy residents belong to this unremarkable category. Our Sun weighs exactly one solar mass by definition. Astronomers literally use it as the standard unit. They measure stellar masses against our ordinary star. Here's where our Sun's mediocrity becomes strikingly apparent. Red supergiant stars scattered throughout our galaxy grow incredibly massive. They'd engulf Jupiter's entire orbit. Betelgeuse could completely swallow Earth-Mars, and the asteroid belt, it would still have room to spare. Blue hypergent stars burn with incredible intensity. They outshine our Sun by millions to one. These stellar celebrities consume nuclear fuel rapidly. They explode in spectacular supernovae after brief lifetimes. Meanwhile, tiny red dwarf stars compose 75% of our stellar population. They burn fuel so efficiently they'll outlast our Sun by trillions of years. Many red dwarfs will continue shining long after our Sun dies. They'll outlive our Sun's transformation into a cold white dwarf remnant. Even our Sun's eventual death will prove utterly unremarkable. No dramatic explosion. No spectacular cosmic finale. Just a gradual fade into stellar retirement. Yet this completely ordinary star managed something extraordinary. It created perfect conditions for planetary formation. Perfect conditions for complex life to emerge. The Sun's steady energy output has remained stable within 1% for over 4 billion years. This reliability allows liquid water to exist on Earth's surface. It allows this existence across geological timescales. More dramatic stars would have either fried their planets or provided insufficient energy. Life couldn't develop under such conditions. Yellow stars like ours represent the galaxy's reliable middle class. Stable, long-lived, and thoroughly predictable. We orbit cosmic middle management in a galaxy filled with genuine stellar superstars. Sometimes the most average things produce the most extraordinary results. In this case, stellar mediocrity enabled something incredible. The emergence of planets, oceans, and eventually life itself. Boring can be surprisingly magical. Every morning, sunlight streams through your window. It completes the universe's most remarkable delivery journey. That warm glow on your face traveled 150 million kilometers through vacuum. But here's what makes this daily delivery truly extraordinary. The light hitting your skin right now began its journey exactly 8 minutes and 20 seconds ago. Nothing in the universe moves faster than this cosmic express service. Ancient philosophers assumed light traveled instantaneously. They believed vision worked through beams shooting from human eyes. These beams supposedly illuminated distant objects. This misconception persisted for centuries. Then Danish astronomer Ole Armer made careful observations in 1676. He studied Jupiter's moons and noticed something peculiar. When Earth moved farther from Jupiter during its yearly orbit, the moons appeared behind schedule. When Earth moved closer, they seemed ahead of schedule. Armer realized light itself must travel at finite speed. The moons weren't changing their timing. Light simply took longer to reach us across greater distances. This breakthrough revealed light's incredible velocity. It races through space at approximately 300,000 kilometers per second. That speed seems impossibly fast until you consider cosmic distances. Light can circle Earth's equator over 7 times in just 1 second. Yet it still requires 8 minutes and 20 seconds to cross the Sun-Earth gap. This creates a fascinating temporal disconnect. The sun you see in your sky shows how our star appeared over 8 minutes ago. You never see the sun's current state, always its recent past. This light speed limit creates profound implications for space exploration. Radio signals sent to Mars take between 4 and 24 minutes. The timing depends on planetary positions. Conversations with astronauts on Mars would involve lengthy delays. Commands sent to outer solar system spacecraft take hours to arrive. The Voyager probes now require over 22 hours for signals to reach Earth. Yet photons streaming from the sun's surface began an even more incredible journey. They started long before their 8-minute sprint to Earth. These same particles originated as energy released by nuclear fusion, deep within the sun's core. That energy took approximately 100,000 years to reach the surface. It worked its way through countless collisions and absorptions. The sunlight warming your face represents ancient nuclear energy that predates human civilization. Light speed might be the universe's ultimate express service, but even express delivery sometimes requires extended processing time. Deep beneath about 700,000 kilometers of superheated gas lies the ultimate high-security manufacturing facility. No windows, no doors. Security so intense that even light takes 100,000 years to escape. Welcome to the sun's core, the universe's most productive fusion factory. It's been running non-stop for 4.6 billion years without a single coffee break. This cosmic foundry operates under conditions that make Earth's most powerful nuclear reactors look like birthday candles. Temperatures reach 15 million degrees Celsius in the sun's heart. That's 2,700 times hotter than molten lava. Pressure builds to 250 billion times Earth's atmospheric pressure. These crushing conditions force hydrogen nuclei together. They overcome their natural electrical repulsion. Every single second, this stellar factory processes 600 million tons of hydrogen fuel. That's equivalent to converting Mount Everest into pure energy every 2 seconds. Through nuclear fusion, 4 hydrogen nuclei combine to create 1 helium nucleus. But here's the cosmic accounting trick that powers our solar system. The helium weighs slightly less than the original hydrogen. That missing mass transforms directly into energy. Einstein's famous equation in action. The numbers become staggering when you calculate energy output. Each second, nuclear fusion converts 4 million tons of matter into pure energy. That's like detonating 100 billion hydrogen bombs every heartbeat. This energy production has remained remarkably stable across billions of years. The Sun's core maintains such precise control that output varies by less than 0.1% per century. Here's what makes this fusion factory particularly remarkable. Unlike human-built nuclear reactors, the Sun's core regulates itself automatically. It requires no constant monitoring or control systems. If fusion rates increase slightly, the core expands and cools. This slows the reaction. If rates decrease, gravity compresses the core. This raises temperatures and accelerates fusion. This natural thermostat has kept our neighborhood power plant running reliably, running since before Earth even existed. The Sun contains enough hydrogen fuel to operate this cosmic factory for approximately 10 billion years total. We're currently about halfway through that stellar lifetime. For the next 5 billion years, this buried fusion reactor will continue its work, converting hydrogen into helium while generating steady energy output. This maintains Earth's climate and powers all life on our planet. You think your morning commute is bad? Energy created in the Sun's core faces an epic journey to reach the surface. A cosmic commute that makes your worst rush hour experience look like a leisurely stroll. What should be a simple about 700,000-kilometer trip becomes a 100,000-year odyssey. All thanks to the solar interior's most frustrating neighborhood, the radiation zone. This isn't ordinary traffic. High-energy gamma-ray photons try to escape the Sun's interior. These photons carry nuclear energy from fusion reactions in the core, but they immediately encounter a dense crowd of atomic particles. These particles block their path like the universe's most stubborn construction zone. Every few centimeters, a photon collides with an electron or atomic nucleus. It gets absorbed, then re-emitted in a random direction. The radiation zone extends from the core boundary to about 70% of the Sun's radius. Throughout this region, matter remains so densely packed that photons can't travel straight. Instead, they follow what physicists call a random walk, bouncing back and forth, sideways, even backward toward the core. Imagine trying to walk across a crowded nightclub while blindfolded and drunk. That's basically how energy moves through the radiation zone. Scientists calculated this incredible journey time using statistical physics. A photon travels at light speed between collisions, but it changes direction randomly with each interaction. The mathematics of random walks shows a startling result. Covering 500,000 kilometers through such dense material requires an average of 100,000 years. Some particularly unlucky photons might take over 1 million years. They're trying to complete their escape attempt. This creates a fascinating temporal disconnect. The light hitting your face right now began its journey as nuclear energy when early humans learned to use stone tools. That warming sunlight predates the rise and fall of entire civilizations. The Sun's surface currently releases energy generated during the last ice age. But here's where the story gets even more remarkable. Once photons finally reach the outer 30% of the Sun, everything changes. They enter a completely different transportation system. The convection zone operates like a cosmic express elevator, carrying energy to the surface in just days or weeks. This dramatic change occurs because outer solar material becomes hot enough to rise. Massive circulation currents form, finally giving those ancient photons a fast ride to freedom. The Sun's outer layer operates like the universe's largest lava lamp, complete with bubbling blobs of superheated gas, rising and falling in endless circulation patterns. But this isn't some gentle aquarium decoration. We're talking about convection cells the size of Texas, churning molten material at temperatures that would vaporize any known substance. These cosmic bubbles create a granular texture on the sun's surface. It looks remarkably like scattered rice grains when viewed through powerful telescopes. Ancient astronomers could never have imagined this hidden solar architecture. They saw a smooth, perfect disk gliding across their skis. Only when high-resolution telescopes revealed the sun's surface in extraordinary detail did scientists discover something shocking. The solar surface appears covered with tiny bright polygons. Dark boundaries separate each bright cell. Each bright cell measures about 1,000 kilometers across. That's roughly the distance from New York to Chicago. These granules represent the tops of massive convection currents. Hot material rises through the center of each cell. It spreads horizontally across the surface, then sinks back down along cooler boundaries. The entire pattern constantly shifts and evolves. Individual granules last only 8 to 20 minutes before dissolving. New ones replace them continuously. The sun's surface essentially boils like a pot of cosmic oatmeal. The physics driving this convection would humble any earthly heat engine. Rising material emerges at temperatures around 6,000 degrees Celsius, hot enough to melt any metal instantly. As this material spreads across the surface, it cools by about 300 degrees. It becomes denser. Gravity then pulls the cooled gas back down into the interior. There it heats up again and begins another circulation cycle. What makes solar convection particularly impressive is its incredible efficiency. This bubbling process transports energy from the deep interior to the surface in just weeks. Compare this to the 100,000-year journey through the radiation zone below. The convection zone acts like a cosmic express delivery service. It rapidly moves energy the final 200,000 kilometers to the surface. There it can radiate into space. Interestingly, the sun's convection operates on multiple scales simultaneously. Beyond the small rice grain granules, astronomers have discovered supergranules. These measure 30,000 kilometers across and persist for about 24 hours. Even larger circulation cells may extend throughout the entire convection zone. The sun essentially runs a multi-layered bubble machine. It efficiently delivers nuclear energy from its core to the surface. There it can warm planets throughout the solar system. Step outside on a sunny day and feel warmth on your skin. That gentle heat traveled across 150 million kilometers of empty space. It came from a thin layer astronomers call the photosphere, literally meaning sphere of light. This represents the sun's visible surface, the bright disk we see in our sky. Yet calling it a surface is somewhat misleading. The sun contains no solid boundary at all. Instead, the photosphere marks the altitude where solar gas finally becomes transparent. Light can escape into space at this level. Early astronomers assumed the sun must have a solid surface like Earth or the Moon. This reasonable assumption persisted until spectroscopy revealed the sun's true gaseous nature. When scientists finally measured the photosphere's properties precisely, they discovered it operates at about 5,800 degrees Celsius. That's nearly hot enough to boil iron. Yet this represents the coolest layer in the entire solar atmosphere. The photosphere spans roughly 500 kilometers in thickness, thinner than the distance from Boston to Philadelphia. Within this relatively narrow shell, gas density drops dramatically, from thick to transparent. Below the photosphere, solar material remains too opaque for light to penetrate. Above it, gas becomes so thin we can see through it to the photosphere beneath. This creates the sharp boundary we perceive as the sun's edge. Despite being called the solar surface, the photosphere churns with constant activity. The granulation pattern from underlying convection covers the entire photosphere, constantly shifting bright and dark cells. Sunspots appear as dark blemishes where strong magnetic fields temporarily cool local temperature by about 1500 degrees. Solar flares occasionally erupt from the photosphere, releasing more energy in minutes than human civilization consumes in years. The light spectrum emitted by the photosphere tells us everything we know about the sun's composition. When this light passes through a spectrometer, it reveals thousands of dark absorption lines. Different elements absorb specific wavelengths. These stellar fingerprints allow astronomers to determine that the sun consists of roughly 73% hydrogen, 25% helium, and 2% heavier elements by mass. Here's what makes the photosphere particularly crucial for life on Earth. This thin layer determines the exact amount of energy radiating toward our planet. The photosphere's temperature and surface area combine to produce the solar power that maintains Earth's climate. A temperature change of just 100 degrees in the photosphere would dramatically alter Earth's energy budget. It could trigger ice ages or runaway warming. We depend entirely on this distant layer of hot gas maintaining precise energy output across geological timescales. Here's a puzzle that has stumped solar physicists for over a century. You'd expect temperatures to decrease steadily as you move away from any heat source. Walk away from a campfire and it gets cooler. The same logic should apply to the sun. But something utterly bizarre happens in the solar atmosphere, something that violates common sense and challenges our understanding of basic physics. The sun's visible surface operates at a relatively modest about 5,800 degrees Celsius. Move outward just a few thousand kilometers and you encounter the corona, a shimmering atmosphere that blazes at over 1 million degrees Celsius. That's nearly 200 times hotter than the surface below. It's like discovering that air above a candle flame somehow burns 200 times hotter than the candle itself. This temperature inversion shouldn't be possible according to normal heat transfer. Early solar observers noticed this strange atmospheric layer during total solar eclipses. When the moon blocks the blinding photosphere, a beautiful silvery crown becomes visible. It extends millions of kilometers into space. 19th century astronomers assumed this corona consisted of cool gas, gently illuminated by reflected sunlight. This comforting assumption would be demolished when scientists finally measured the corona's actual temperature. Spectroscopic analysis revealed emission lines from highly ionized iron atoms. These spectral signatures only appear at temperatures exceeding 1 million degrees Celsius. The corona wasn't cool reflected light at all. It was superheated plasma hot enough to strip electrons from iron nuclei, creating conditions more extreme than the sun's own surface. Scientists suddenly faced an apparently impossible situation. This violated fundamental thermodynamics. Multiple theories attempt to explain this coronal heating puzzle. Magnetic reconnection events might explosively release stored magnetic energy throughout the corona. Acoustic waves generated by surface convection could carry energy upward. They deposit heat through turbulent dissipation. Tiny magnetic field fluctuations might constantly inject energy into coronal plasma through a process called magnetic braiding. But here's the frustrating truth. After decades of intensive research using space-based solar observatories, scientists still can't definitively explain this. They still can't explain how the corona maintains its million-degree temperature. The Parker Solar Probe, launched in 2018, is providing the first direct measurements from within the coronal itself. This mission might finally solve the mystery, a mystery that has confounded solar physics since the late 1800s. Until then, the corona remains one of our nearest star's most humbling unsolved puzzles. A million-degree reminder that the sun still holds secrets we don't understand. Ancient alchemists dreamed of transforming lead into gold. They never imagined that stars routinely perform far more spectacular transformations. The sun converts the universe's simplest element into the second simplest. But it accomplishes this feat under conditions so extreme they defy human experience. Deep within the sun's core, nature performs the ultimate magic trick. 4 separate hydrogen nuclei somehow overcome their mutual hatred. They fuse together to create something completely different: a single helium nucleus. This isn't gentle chemistry happening in a test tube. This represents violent atomic collision at temperatures that would vaporize any earthly material. Yet this cosmic alchemy follows Einstein's most famous equation with mathematical precision. Here's where Einstein's E=mc² equation reveals its cosmic significance. When 4 hydrogen nuclei combine to form 1 helium nucleus, they fuse into something completely different. The helium weighs slightly less than the original hydrogen. About 0.7% of the original mass simply disappears. That vanished matter doesn't violate physics. It transforms directly into pure energy according to Einstein's mass-energy equivalence principle. Hydrogen nuclei naturally repel each other through electrical force. Getting them close enough to fuse requires temperatures exceeding 10 million degrees Celsius. The numbers become mind-boggling when you calculate the energy release. Each gram of hydrogen fuel that undergoes complete fusion produces 30 billion joules of energy. That's equivalent to burning 20 tons of coal or detonating 15 tons of TNT. The sun processes 600 million tons of hydrogen every second through this fusion process. No wonder our neighborhood star outshines everything else in the solar system combined. This nuclear transformation occurs through a complex sequence called the proton-proton chain. First, 2 hydrogen nuclei collide with enough violence to overcome electrical repulsion. 1 proton transforms into a neutron through radioactive decay. This creates a deuterium nucleus. This deuterium then fuses with another hydrogen nucleus to form helium-3. Finally, 2 helium-3 nuclei collide and fuse. They produce helium-4 plus 2 leftover hydrogen nuclei. These start the process again. What makes this cosmic alchemy particularly remarkable is its incredible efficiency. Nuclear fusion converts matter into energy with nearly 100 times more efficiency than chemical combustion. If cars could somehow run on hydrogen fusion instead of gasoline, a single gram of fuel would power your vehicle for over 100,000 kilometers. The sun has been operating this ultimate power source continuously for 4.6 billion years. This proves that fusion represents the universe's preferred method for generating stellar energy. Every single day, something extraordinary happens inside our sun. Something slightly terrifying. 4 million tons of solid matter simply vanish from existence. Not hidden, not transformed into other matter, completely annihilated. This mass converts directly into the light and heat that warm your morning coffee. The sun literally destroys itself to keep you comfortable. It has been doing so for billions of years without pause. This cosmic disappearing act occurs through the mass-energy conversion described by Einstein's famous equation. When nuclear fusion creates helium from hydrogen, The final product weighs slightly less than the original ingredients. That missing mass doesn't disappear mysteriously. It becomes the energy that powers our solar system. Every second, fusion reactions in the Sun's core erase 4 million tons of matter from the universe. To grasp this scale, imagine Mount Everest completely vaporized every 2 seconds. That's roughly equivalent to the mass disappearing from the Sun through fusion reactions. The mountain wouldn't crumble or melt. It would simply cease to exist, transformed into pure energy racing outward at the speed of light. This process continues relentlessly, second after second, year after year, across billions of years. The energy produced by this mass conversion defies human comprehension. Each second, the Sun generates about 3.8 times 10 to the 26 watts of power. Written out in full, that number contains 26 zeros. To put this in perspective, the Sun produces more energy in 1 second than human civilization has consumed throughout our entire history. All our fires, engines, power plants, and nuclear reactors combined represent less than 1 second of solar output. Here's what makes this mass destruction particularly fascinating. Despite losing 4 million tons every second, the Sun contains so much material that this weight loss barely registers. The Sun weighs approximately about 2 times 10 to the 30 kilograms. At the current rate of mass conversion, the Sun would need to operate for 150 million years to lose just 0.1% of its total weight. Our star possesses enough mass to continue this fusion process for another 5 billion years. This constant mass-to-energy conversion creates a fascinating cosmic paradox. The Sun simultaneously represents both the ultimate example of matter and the ultimate generator of pure energy. Every photon streaming from its surface began as actual mass deep within the solar core. The warmth on your face consists of matter that used to be part of the Sun itself. In a very real sense, we're all powered by stellar cannibalism, the Sun consuming itself to energize the solar system. Take every coal plant, nuclear reactor, hydroelectric dam, and solar panel on Earth. Add every car engine, airplane turbine, and power generator humans have ever built. Include every campfire, candle, and birthday cake flame that has ever burned throughout history. The Sun produces more energy in 1 second than this entire collection could generate in several lifetimes. This cosmic power plant operates on a scale that makes human energy production look like striking matches in a thunderstorm. The Sun outputs about 3.8 times 10 to the 26 watts continuously. To match just 1 second of solar energy production, you'd need to operate every power plant on Earth simultaneously for about 4 million years. The Sun casually generates more power than our entire species has ever harnessed. It does this every heartbeat for billions of years. Scientists calculated these staggering numbers by measuring solar energy reaching Earth's upper atmosphere. Our planet receives approximately about 1.74 times 10 to the 17 watts of solar power. That's enough to meet global energy demands 10,000 times over. Yet Earth intercepts only about 45 billionths of a percent of the Sun's total output. The vast majority of solar energy radiates uselessly into empty space, never warming a single planet or powering any civilization. This energy abundance creates a humbling perspective on human energy consumption. The fossil fuels we've burned since the Industrial Revolution represent stored solar energy from millions of years ago. Ancient plants captured sunlight through photosynthesis. Then geological processes compressed this organic matter into coal and oil. We're essentially burning concentrated sunshine from the distant past. Yet all the fossil fuels ever extracted equal less than 2 days of current solar output. Modern renewable energy attempts to tap this cosmic power source directly. The most efficient solar panels convert about 22% of incident sunlight into electricity. Even with this relatively low efficiency, covering just 0.3% of Earth's land surface with solar panels would meet global electricity demands. The sun delivers so much energy to Earth that we could power our entire technological civilization using a tiny fraction of available solar radiation. What makes the sun's power output truly staggering is its incredible consistency. This stellar furnace has maintained roughly the same energy production for billions of years. During Earth's entire geological history, solar output has varied by less than 30%. Human power plants require constant maintenance, refueling, and replacement. The sun just keeps burning, decade after decade, generating more energy every second than our species has consumed since we discovered fire. Most power sources eventually run out. Campfires consume wood, cars burn gasoline, even nuclear reactors require fresh fuel rods. But the sun operates with a fuel supply so vast it challenges human comprehension of time itself. Our neighborhood star contains enough hydrogen to maintain its current energy output for approximately 10 billion years total. We're currently enjoying the middle-aged phase of a stellar lifetime that spans geological eras. To understand this incredible fuel longevity, consider the sun's hydrogen inventory. Roughly 73% of solar mass consists of hydrogen, the universe's most abundant element and perfect fusion fuel. This represents about 1.4 times 10 to the 30 kilograms of hydrogen waiting to be converted into helium through nuclear fusion. Even burning 600 million tons of hydrogen every second, this fuel supply will last longer than complex life has existed on Earth. The sun formed 4.6 billion years ago when a collapsing gas cloud accumulated enough mass to ignite nuclear fusion in its core. Since then, it has been steadily converting hydrogen into helium while maintaining remarkably stable energy output. Stellar evolution models predict the sun will continue its current hydrogen-burning phase for another 5 billion years. That's before transitioning into its red giant phase. That's enough time for continental drift to completely rearrange Earth's geography multiple times over. This extraordinary fuel efficiency results from the sun's massive size and precisely controlled fusion rate. Unlike explosive fusion in hydrogen bombs, stellar fusion proceeds at carefully regulated speeds. The speeds are determined by core temperature and pressure. The sun essentially operates like a gigantic thermostat. If fusion rates increase slightly, the core expands and cools. This slows the reaction. If rates decrease, gravity compresses the core. This raises temperatures and accelerates fusion. Here's what makes solar fuel longevity particularly remarkable when compared to human energy sources. All recoverable fossil fuel reserves on Earth represent roughly 10 to the 22 joules of stored energy. The sun generates this same amount of energy in approximately 35 minutes. Our planet's entire fossil fuel endowment equals less than 1 hour of solar output. Meanwhile, the sun's remaining hydrogen fuel could power current solar output for 150 million times longer than human civilization has existed. This vast fuel supply provides comforting cosmic perspective on humanity's long-term energy future. While we debate renewable energy transitions and fossil fuel depletion, our local star quietly maintains a power source that will outlast our species. It will outlast our planet's habitability and possibly life itself. The Sun represents the ultimate example of sustainable energy. A fusion reactor that has been operating reliably for longer than complex life has existed. It will continue doing so for billions of years into the future. For over 70 years, scientists have been chasing humanity's most ambitious dream, recreating the Sun's nuclear fusion process here on Earth. This quest represents the ultimate attempt to capture stellar power and solve our energy problems forever. Yet building an artificial star has proven far more challenging than splitting atoms or landing on the moon. The physics that seem effortless inside stellar cores become extraordinarily difficult to replicate in earthly laboratories. The fundamental challenge lies in the extreme conditions required for nuclear fusion. Hydrogen nuclei need temperatures exceeding 100 million degrees Celsius to overcome their electrical repulsion. They must fuse together at these impossible temperatures. At these temperatures, electrons separate completely from nuclei. This creates a state of matter called plasma that doesn't exist naturally on Earth. This plasma must be confined at enormous pressures while maintaining fusion-enabling temperatures. It's like trying to hold a piece of the Sun's interior inside a magnetic bottle. Current fusion experiments use two main approaches to achieve these stellar conditions. Magnetic confinement fusion uses powerful magnetic fields to contain superhot plasma in donut-shaped chambers. These are called tokamak reactors. Inertial confinement fusion blasts tiny fuel pellets with intense laser beams. This compresses hydrogen to stellar densities for brief moments. Both methods can achieve fusion reactions, but neither has yet produced more energy than it consumes. The engineering challenges become apparent when you compare earthly fusion attempts to solar conditions. The Sun's core achieves fusion through gravitational pressure 250 billion times stronger than Earth's atmosphere. Laboratory reactors must compensate for weaker gravity by using much higher temperatures, often 5 to 10 times hotter than the solar core. This creates materials science problems that push technology beyond current limits. No known material can withstand direct contact with 100 million degree plasma. Recent breakthrough experiments have brought fusion energy closer to reality. In December 2022, scientists at the National Ignition Facility achieved fusion ignition. They produced more energy from fusion reactions than the laser energy delivered to the fuel pellet. This represents the first time humans have created net energy gain from controlled nuclear fusion. While this milestone proves fusion energy is physically possible, scaling up to practical power generation will require decades of additional development. The potential rewards justify this enormous scientific effort. A fusion power plant would burn deuterium and tritium, heavy forms of hydrogen that can be extracted from seawater. The fusion fuel in one bathtub of seawater contains energy equivalent to 300 gallons of gasoline. Fusion produces no carbon emissions, no long-lived radioactive waste, and no possibility of meltdown accidents. If humans can master controlled fusion, we'll essentially have built our own miniature suns to power civilization with clean, abundant energy for millions of years. Yet the Sun makes this process look deceptively simple. Our star has been operating a stable fusion reactor for 4.6 billion years using nothing but gravity and hydrogen. Meanwhile, human fusion experiments require some of the most sophisticated technology ever developed, just to sustain fusion reactions for minutes or seconds. The Sun remains our ultimate teacher in the art of controlled nuclear fusion, a stellar masterclass we're still struggling to understand and replicate. For centuries, astronomers viewed the sun as an unblemished golden disk. It glided serenely across the sky like celestial perfection. Then telescopes revealed an uncomfortable truth. Our supposedly perfect star regularly breaks out in dark spots scattered across its surface, like cosmic acne. These weren't instrument defects or atmospheric distortions. The sun actually grows temporary blemishes that come and go with mysterious regularity. These dark patches, called sunspots, appear black only by comparison to the blazing solar surface surrounding them. In reality, sunspots glow at temperatures around 4,000 degrees Celsius, hot enough to vaporize any earthly material instantly. They look dark because they're about 1,500 degrees cooler than the normal photosphere temperature. It's like comparing a red-hot ember to a white-hot furnace. Both will burn you severely, but one appears dim next to the other. Sunspots form where powerful magnetic fields erupt through the solar surface. Like invisible weeds breaking through concrete, these magnetic field lines are thousands of times stronger than Earth's magnetic field, powerful enough to levitate a paperclip at close range. When concentrated magnetic fields push through the photosphere, they suppress normal convection currents. These currents carry heat from the solar interior. This creates cooler regions that appear as dark spots when viewed from Earth. Individual sunspots can grow larger than entire planets. The biggest sunspots stretch over 50,000 kilometers across, wide enough to swallow 4 Earths side by side. These magnetic monsters typically appear in pairs or complex groups, connected by invisible magnetic field lines arching through the solar atmosphere. Material flows along these magnetic highways, creating spectacular loops and bridges visible in specialized solar telescopes. What makes sunspots particularly fascinating is their temporary nature. Small spots may last only hours or days before dissolving back into the normal solar surface. Larger sunspot groups can persist for weeks or months. They rotate across the solar disk with the sun's 25-day rotation period. But eventually, all sunspots fade away. Their magnetic fields weaken and allow normal convection to resume. The sun's surface heals itself like cosmic skin regenerating after injury. Ancient Chinese astronomers recorded sunspots over 2,000 years ago during periods when atmospheric haze made direct solar observation possible. European astronomers rediscovered them when Galileo first pointed telescopes at the sun in the early 1600s. This revelation shocked the scientific community. The sun wasn't supposed to have imperfections. These dark blemishes represented the first evidence that our supposedly unchanging star actually experiences dynamic, evolving activity that varies over time. The sun operates like the universe's most predictable mood ring. It cycles between periods of calm stability and magnetic chaos with clockwork regularity. This isn't random stellar behavior. Our neighborhood star follows an 11-year activity cycle, so precise that astronomers can predict when the next peak will occur decades in advance. During quiet periods, the solar surface appears relatively smooth with few sunspots. During active periods, the sun erupts with dozens of sunspot groups, spectacular flares, violent magnetic outbursts. This solar cycle was discovered by Heinrich Schwabe, a German amateur astronomer who spent 17 years patiently counting sunspots every clear day from 1826 to 1843. What started as a casual hobby revealed one of astronomy's most important patterns. Schwabe noticed that sunspot numbers weren't random at all. They rose and fell in a regular rhythm, reaching maximum abundance roughly every 11 years before declining to minimum levels, then beginning the cycle again. The sunspot cycle reflects deeper changes in the sun's magnetic field structure. During solar minimum, the sun's magnetic field resembles a simple bar magnet, with north and south poles. As the cycle progresses towards solar maximum, the magnetic field becomes increasingly complex and tangled. Magnetic field lines twist and stretch until they snap like overstressed rubber bands, creating the sunspots, flares, and other energetic phenomena that characterize solar maximum. Solar cycle 25 began in December 2019. This marks the start of the sun's most recent journey from quiet to active phase. Astronomers predict this cycle will peak around 2025, when monthly sunspot numbers should reach their highest levels. During peak activity, the sun may display 100 or more sunspots simultaneously. Compare this to days or weeks without any visible spots during solar minimum periods. What makes this cycle particularly remarkable is its incredible consistency across centuries of observation. Despite operating as a nuclear furnace under impossible physical conditions, the sun maintains this 11-year rhythm with the reliability of cosmic clockwork. The cycle duration varies slightly. It sometimes lasts 9 years and occasionally stretches to 13 years, but it always returns. Astronomers have traced this pattern back over 400 years using historical sunspot records. They can detect signs of similar cycles in tree rings and ice cores spanning thousands of years. This predictable cycle has practical implications for modern technology. Satellites, power grids, and communication systems all experience increased interference during solar maximum periods. Space agencies plan mission launches around the solar cycle to minimize radiation exposure for astronauts. Even airline pilots adjust flight routes over polar regions during periods of high solar activity. Our technological civilization has learned to dance around the sun's predictable mood swings. Every few hours during periods of high solar activity, something extraordinarily violent happens on the sun's surface. Twisted magnetic field lines suddenly snap like cosmic rubber bands under impossible tension. They release more energy in minutes than human civilization consumes in years. These magnetic explosions, called solar flares, represent some of the most energetic events in the solar system. They are stellar temper tantrums that can disrupt technology across Earth from 150 million kilometers away. Solar flares occur when magnetic field lines become twisted into unstable configurations around sunspot groups. These magnetic structures store enormous amounts of energy, like coiled springs under extreme pressure. When the magnetic stress becomes too great, the field lines suddenly reconnect in violent explosions. They accelerate particles to near light speed and heat plasma to temperatures exceeding 20 million degrees Celsius. The largest solar flares release energy equivalent to billions of hydrogen bombs exploding simultaneously. The most powerful flare ever recorded occurred on November 4, 2003. It saturated X-ray detectors on multiple spacecraft. Scientists estimate this monster flare released approximately 10 to the 32 joules of energy. It was roughly equal to burning all fossil fuel reserves on Earth every second for an entire year. Yet this cataclysmic explosion represented less than 0.01% of the sun's normal energy output. These stellar explosions unfold with breathtaking speed. The initial energy release occurs within minutes, but the effects ripple outward for hours. Intense X-rays and ultraviolet radiation race toward Earth at light speed, arriving just 8 minutes after the explosion. High-energy particles follow more slowly, reaching Earth in 30 minutes to several hours depending on their energy levels. Finally, shock waves propagate through the solar wind, potentially triggering geomagnetic storms when they encounter Earth's magnetosphere. Modern technology has learned to fear solar flares. The intense radiation can blind satellite sensors, disrupt GPS signals, force astronauts to shelter in protected areas of the International Space Station. Radio communications become unreliable as flare radiation ionizes Earth's upper atmosphere. Power grids experience voltage fluctuations from induced electrical currents. During extreme events, entire electrical networks can collapse, leaving millions without power for days or weeks. The 1859 Carrington event provides a sobering example of solar flare impacts. This massive flare caused telegraph systems worldwide to fail. Some operators received electric shocks from their equipment. Telegraph lines sparked and caused fires. Aurora displays appeared as far south as the Caribbean. If a similar event occurred today, it could cause trillions of dollars in damage to our electronically dependent civilization. Space weather forecasters now monitor the sun constantly, providing warnings when dangerous flares erupt from active sunspot regions. Occasionally, the sun decides that solar flares aren't dramatic enough. During particularly violent magnetic explosions, our star launches billion-ton cannonballs of superheated plasma directly into space. These projectiles race at speeds exceeding 1,000 kilometers per second. These cosmic projectiles, called coronal mass ejections or CMEs, represent the sun's most spectacular artillery display. Stellar ammunition that can travel across the entire solar system and occasionally score direct hits on Earth. CMEs form when magnetic explosions are powerful enough to completely eject part of the solar corona into space. Unlike solar flares that primarily release energy and radiation, coronal mass ejections hurl actual solar material across interplanetary space. A typical CME contains 1 to 5 billion tons of plasma, roughly equivalent to launching Mount Everest into space at supersonic speeds. The ejected material consists of electrons, protons, and heavier atomic nuclei heated to millions of degrees. These plasma projectiles travel through space like invisible bullets, taking 1 to 5 days to reach Earth, depending on their initial velocity. The fastest CMEs can cross the Sun-to-Earth distance in just 15 hours, racing through the solar system at over 2,000 kilometers per second. Slower ejections lumber across interplanetary space at more modest speeds, 300 to 500 kilometers per second. Either way, billions of tons of solar material eventually arrive at Earth's doorstep, like cosmic pizza delivery. When a CME collides with Earth's magnetosphere, the results can be spectacular. The impact compresses our planetary magnetic field and injects enormous amounts of energy into the magnetospheric system. This triggers intense geomagnetic storms that send charged particles cascading into Earth's upper atmosphere. The colliding particles create brilliant aurora displays that can extend far from their normal polar regions. During extreme events, aurora have been visible from as far south as Mexico and the Mediterranean. But CME impacts also pose serious threats to modern technology. The changing magnetic fields induce electrical currents in long conductors, power transmission lines, and oil pipelines. These induced currents can overload electrical equipment and cause widespread blackouts. In March 1989, a major CME caused a complete power grid collapse in Quebec, leaving 6 million people without electricity for 9 hours. Satellite electronics are particularly vulnerable. Many spacecraft experience temporary malfunctions or permanent damage during severe geomagnetic storms. Space agencies now track CMEs using specialized spacecraft positioned between Earth and the Sun. When dangerous plasma projectiles launch from solar-active regions, mission controllers can warn satellite operators and power companies. They take protective measures. Astronauts on the International Space Station receive advance warning to shelter in heavily shielded areas. Even airline pilots adjust flight routes to avoid increased radiation exposure during major geomagnetic storms. The Sun's billion-ton plasma cannons have taught our technological civilization to respect the power of stellar artillery. Right now, as you read this, you're sitting inside the largest single structure in our solar system. It's completely invisible, weighs almost nothing, yet extends far beyond Pluto's orbit to create a massive bubble encompassing everything we've ever called home. This enormous region, known as the heliosphere, forms where the solar wind pushes against the interstellar medium, like a cosmic snowplow creating a protective cavity in space. The solar wind doesn't blow like Earth's weather. Instead, it consists of electrons and protons streaming away from the solar corona at speeds between 300 and 800 kilometers per second. This particle flow originates from the corona's million-degree temperature, which provides enough thermal energy for gas to escape the sun's gravitational pull entirely. Every second, the sun loses about 1 million tons of material through this solar wind, a cosmic bleeding that has continued for billions of years. This invisible particle stream carries the sun's magnetic field throughout the entire solar system, creating what scientists call the interplanetary magnetic field. Solar wind particles follow magnetic field lines like cars on invisible highways, spiraling outward from the sun while rotating with the solar system's 25-day period. This creates a distinctive pattern resembling the water spray from a rotating garden sprinkler, magnetic field lines that curve gracefully through interplanetary space. The heliosphere forms where solar wind pressure balances against the interstellar medium, the thin gas and dust between stars. At this boundary, roughly 120 times Earth's distance from the Sun, the solar wind finally slows down. It begins mixing with interstellar particles. The resulting structure resembles a giant teardrop shape with the Sun at its center, compressed on the side facing our solar system's motion through the galaxy, stretched into a long tail on the opposite side. This solar wind bubble serves as our cosmic neighborhood's first line of defense against galactic cosmic rays, high-energy particles from distant stellar explosions that could prove harmful to life. The heliosphere deflects about 75% of these cosmic rays away from the inner solar system, reducing radiation levels throughout the region where planets orbit. Without this protection, Earth would experience much higher cosmic ray bombardment. This could damage the ozone layer and increase surface radiation. The Voyager spacecraft provided our first direct measurements from beyond the heliosphere. They crossed into interstellar space in 2012 and 2018. These robotic ambassadors confirmed that our solar wind creates a genuine boundary between solar system space and the galaxy beyond. We literally live inside a bubble blown by our own star, a cosmic safe haven carved from interstellar space by billions of years of solar wind. The sun doesn't just warm and illuminate our neighborhood, it actively shapes the space around us, creating the largest architectural feature in our local cosmic environment. Venus is too hot, Mars is too cold, but Earth sits in the universe's most exclusive neighborhood. It is a narrow band around the sun where temperatures remain just right for liquid water to exist on planetary surfaces. This isn't cosmic luck. It's a precise orbital sweet spot. So narrow, shift Earth's position by just 5% either way, and it spells disaster. Our blue marble would transform into either a lifeless ice ball or a scorching hellscape like our neighboring worlds. Astronomers call this perfect distance range the habitable zone. Many prefer the more whimsical name Goldilocks zone. It comes from the fairy tale character who preferred things neither too hot nor too cold, but just right. Around our Sun, this zone extends from about 0.9 to 1.5 astronomical units. That is roughly in 35 to 225 million kilometers from our star. Earth orbits right in the middle of this range at 150 million kilometers. It may be the most fortunate cosmic address in the galaxy. The boundaries of this habitable zone aren't arbitrary lines drawn by optimistic astronomers. They represent genuine physical limits determined by planetary atmospheric physics. Move a planet closer than the inner edge. Solar radiation becomes intense enough to trigger a runaway greenhouse effect. Water vapor in the atmosphere traps heat so efficiently that oceans boil away completely. It leaves behind a furnace world shrouded in steam. Venus demonstrates this fate perfectly with surface temperatures reaching 462 degrees Celsius. Drift beyond the outer boundary of the habitable zone, and the opposite catastrophe occurs. Insufficient solar energy reaches the planet's surface to maintain liquid water. The planet enters a runaway icehouse effect where water freezes solid. This increases the surface's reflectivity and causes even more heat to bounce back into space. Mars shows us this frozen destiny. Its polar ice caps and underground permafrost mark the grave of ancient oceans that once flowed across its surface. What makes Earth's position particularly remarkable is how this Goldilocks zone has remained stable for billions of years. This is despite gradual changes in solar output. Young stars typically burn about 30% dimmer than middle-aged stars like our current Sun. Nuclear fusion continues in stellar cores. Stars gradually brighten over geological timescales. Earth has somehow remained within the habitable zone throughout this entire stellar evolution. It has maintained liquid oceans for over 3.8 billion years. This orbital stability has allowed life to emerge, evolve, and flourish across deep time. Complex chemistry requires liquid water as a solvent for biological reactions. Cells need water to transport nutrients and waste products. DNA and protein structures depend on water's unique properties to maintain their intricate molecular architectures. Without liquid water, life as we know it simply cannot exist. Earth's perfect position in the Goldilocks zone has provided the essential foundation for 4 billion years of biological evolution. It makes our planet the only known world where life has gained a permanent foothold in the cosmos. Every blade of grass performs a feat of molecular engineering that makes human technology look primitive by comparison. Through photosynthesis, plants capture photons that traveled 150 million kilometers from the Sun's core. They convert this stellar energy into chemical fuel with an efficiency that would make any engineer jealous. This biological solar power system has been quietly revolutionizing Earth's atmosphere and powering the entire food web for over 3 billion years. The photosynthesis process operates like the world's most sophisticated chemical factory. It uses sunlight to split water molecules and combine the resulting hydrogen with carbon dioxide from the air. This creates glucose, biological fuel that powers cellular metabolism. It releases oxygen as a byproduct. The chemical equation seems deceptively simple. Carbon dioxide plus water plus sunlight equals glucose plus oxygen. Yet this reaction requires some of the most complex molecular machinery ever evolved. Inside every plant cell, microscopic structures called chloroplasts house the photosynthetic equipment. These cellular power plants contain billions of chlorophyll molecules precisely arranged to capture sunlight across specific wavelengths. When photons strike chlorophyll, they knock electrons loose from their atomic orbits. This initiates a cascade of chemical reactions. It ultimately stores solar energy in the bonds of glucose molecules. It's like having millions of tiny solar panels working together inside each leaf. The efficiency of this biological energy conversion astounds scientists. Modern photovoltaic cells convert roughly 20% of incident sunlight into electricity under ideal conditions. Plants typically achieve 3 to 6% efficiency in converting solar energy to stored chemical energy. But they accomplish this while building their own structures. They reproduce and maintain complex cellular metabolism. No human technology can match this combination of energy conversion, self-repair, and reproduction. Photosynthesis has literally transformed our planet's atmosphere over geological time. Early Earth's atmosphere contained virtually no oxygen. Cyanobacteria began releasing oxygen as a waste product around 3.5 billion years ago. These were primitive photosynthetic organisms. This oxygen initially poisoned most existing life forms. It caused the first major extinction event in Earth's history. But eventually, organisms evolved to use oxygen for cellular respiration. This created the oxygen-rich atmosphere that enables complex life today. The global scale of photosynthetic energy conversion dwarfs human energy production. Plants on land and photosynthetic organisms in the oceans capture approximately 130 terawatts of solar power continuously. That is roughly 6 times more energy than human civilization consumes from all sources combined. Every year, photosynthesis converts about 1 in 15 billion tons of carbon dioxide into organic matter while producing 70 billion tons of oxygen. This represents the largest industrial process on Earth. It operates entirely on solar energy and produces no toxic waste. Plants have mastered sustainable energy technology that humans are still struggling to replicate. The sun operates Earth's most impressive public utility. It is a global water recycling system that processes over 500,000 cubic kilometers of water annually. It does this without requiring pipes, pumps, or electricity bills. This cosmic-powered hydrological cycle has been providing fresh water to continents and replenishing ocean levels for billions of years. It works through the simple physics of solar heating and gravitational precipitation. Every morning, solar radiation begins evaporating water from ocean surfaces, lakes, rivers, and soil. This invisible process lifts approximately 1.4 billion tons of water into the atmosphere each day, enough to fill Lake Superior every 6 months. The sun's energy breaks the molecular bonds holding liquid water together. It transforms it into invisible water vapor that rises into the atmosphere. It is like a massive, silent elevator carrying Earth's most precious resource toward the clouds. This solar-powered evaporation process effectively distills seawater on a planetary scale. When water molecules transition from liquid to gas, they leave behind salt, minerals, and pollutants. The atmosphere becomes a gigantic purification system. It carries only pure water vapor inland, where it will eventually condense and fall as fresh precipitation. The sun essentially operates a desalination plant larger than all continents combined. It produces unlimited fresh water from salty oceans. As water-laden air masses move inland, they encounter cooler temperatures or mountain barriers. The invisible vapor condenses around microscopic particles. It forms clouds and precipitation. This process releases the solar energy originally used for evaporation. It warms the atmosphere and drives weather patterns. Every raindrop that falls on your head carries energy that was originally nuclear fusion in the sun's core. It was transported across 150 million kilometers of space. Then it was temporarily stored in atmospheric water vapor. The hydrological cycle redistributes both water and energy across Earth's surface with remarkable efficiency. Tropical regions receive intense solar heating that evaporates vast amounts of water from warm oceans. This water vapor travels to higher latitudes where it condenses and releases heat. It moderates global temperature differences. Meanwhile, precipitation over continents provides the fresh water that fills rivers. It recharges groundwater. It sustains terrestrial ecosystems. Human civilization depends entirely on this solar-powered water delivery system. Agriculture relies on precipitation patterns driven by solar evaporation. Rivers that provide hydroelectric power flow because solar energy lifted water to higher elevations. Gravity can pull it downhill through turbines. Even the groundwater we pump from deep aquifers originally fell as solar-powered precipitation. That was centuries or millennia ago. The sun doesn't just provide light and warmth. It operates the water recycling infrastructure that makes complex life possible on our planet's surface. Long before humans invented clocks, calendars, or smartphones, the sun established Earth's fundamental time management system. This stellar chronometer doesn't just track time. It actively controls the biological rhythms of virtually every living organism on our planet. Life on Earth has synchronized itself to solar rhythms across billions of years of evolution. It runs from the daily sleep cycles of mammals to the seasonal migrations of birds. Earth's 24-hour rotation creates the daily cycle of light and darkness that regulates circadian rhythms in organisms ranging from bacteria to humans. These internal biological clocks evolved to anticipate sunrise and sunset. This allows organisms to optimize their metabolism, reproduction, and behavior around predictable changes in solar energy availability. Plants open their flowers at specific times to attract pollinators. Nocturnal animals emerge after sunset to avoid daytime predators. Even human body temperature, hormone production, and sleep patterns follow circadian cycles tied to solar illumination. The sun's seasonal timekeeper operates through Earth's 23.5 degrees axial tilt as our planet orbits its star. This cosmic geometry creates longer days and more direct sunlight for one hemisphere. It also provides shorter days and weaker illumination for the opposite hemisphere. The resulting seasonal changes in temperature and daylight duration trigger massive biological responses across the entire planet. Trees shed leaves in autumn. Bears enter hibernation. Migratory species travel thousands of kilometers following optimal seasonal conditions. These solar rhythms have become so deeply embedded in life's biology that organisms maintain internal clocks even when isolated from sunlight. Scientists can place plants or animals in constant darkness, yet their metabolisms will continue cycling on roughly 24-hour schedules for days or weeks. This demonstrates that solar timing isn't just environmental conditioning. It's fundamental programming written into the genetic code of terrestrial life. This came through billions of years of evolution under stellar illumination. Modern humans have largely disconnected from these ancient solar rhythms through artificial lighting and climate control. But our biology still responds to the sun's timekeeper. Seasonal affective disorder affects millions of people who receive insufficient sunlight during winter months. Jet lag disrupts circadian rhythms when we travel across time zones faster than our internal clocks can adjust. Shift workers experience health problems when their schedules conflict with natural solar timing patterns. The Sun's role as cosmic timekeeper is remarkable. Its stability is incredible over the long term. Earth's 24-hour rotation period has remained relatively constant for hundreds of millions of years. The seasonal cycle created by our planet's tilted axis has persisted for billions of years with only minor variations. This temporal reliability has allowed life to evolve complex biological rhythms synchronized to solar patterns. Without the Sun's predictable daily and seasonal cycles, Earth's ecosystems would lack the temporal structure that coordinates reproduction, migration, and countless other biological processes. These depend on precise timing. Right now, high-energy particles from distant stellar explosions are racing toward Earth at nearly the speed of light. They carry enough energy to damage DNA and disrupt cellular metabolism. This cosmic radiation bombardment never stops. It's been pelting our solar system for billions of years like invisible machine gun fire from the depths of space. Fortunately, the Sun provides our neighborhood with a massive invisible shield. It deflects roughly 75% of this galactic assault. This creates a protective bubble that makes complex life possible. These cosmic bullets, called galactic cosmic rays, originate from some of the universe's most violent events. Massive stars exploding as supernovae accelerate atomic nuclei to incredible speeds. Neutron-star collisions launch particle streams across interstellar distances. Even distant black holes contribute to this cosmic firing range. They accelerate particles through their powerful magnetic fields. Without protection, this radiation would gradually sterilize planetary surfaces. It would make the evolution of complex life extremely difficult. The Sun's protective mechanism operates through the same solar wind we explored earlier, but it serves a completely different protective function. As the stream of charged particles flowing from our star expands throughout the solar system, it carries the Sun's magnetic field along. It is like an expanding umbrella. This creates what astronomers call the heliosphere. It is a massive magnetic bubble encompassing our entire solar system that extends far beyond Pluto's orbit. When high-energy cosmic rays encounter this solar wind boundary, many get deflected away from the inner solar system entirely. The solar wind essentially blows against incoming cosmic radiation like a stellar hurricane. It reduces the amount of galactic cosmic rays that reach Earth by approximately 75%. During periods of high solar activity, this shielding becomes even more effective. Stronger solar wind creates a more robust barrier against cosmic radiation. Earth receives additional protection from its own magnetic field. It deflects charged particles around our planet like a protective force field. However, this planetary magnetosphere only works effectively because it operates within the Sun's larger heliospheric shield. Without the solar wind reducing cosmic ray flux throughout the solar system, Earth's magnetic field alone would be overwhelmed. It would be overwhelmed by galactic radiation bombardment. The Voyager spacecraft provided dramatic evidence of this solar protection when they crossed into interstellar space beyond the heliosphere. Both probes detected immediate increases in cosmic ray intensity as they passed outside our solar wind bubble. The radiation levels in interstellar space are roughly 4 times higher than within the heliosphere. This demonstrates the effectiveness of our Sun's cosmic radiation shield. This solar protection has been crucial for the development of complex life on Earth. High levels of cosmic radiation would damage the ozone layer. This could allow harmful ultraviolet radiation to reach the surface. The radiation could also directly damage DNA in living organisms. It would increase mutation rates and make the evolution of complex multicellular life much more difficult. The sun doesn't just provide energy for photosynthesis and climate. It actively protects the biosphere from cosmic hazards, could prevent life from flourishing across billions of years. 4.5 billion years ago, in a quiet corner of the Milky Way galaxy, something extraordinary began stirring. A vast cloud of hydrogen gas and cosmic dust stretched across dozens of light years. It contained enough raw material to build thousands of stars like our sun. For millions of years, this cosmic maternity ward remained cold, dark, and seemingly lifeless. Then gravity began its slow, relentless work of stellar construction. The birth process started when a nearby supernova explosion sent shock waves rippling through the molecular cloud, like cosmic labor pains. These stellar explosions compressed parts of the gas cloud beyond a critical threshold. They triggered gravitational collapse in multiple regions simultaneously. Our future solar system began as just one small knot of slightly denser material within this vast stellar factory. Once gravity gained the upper hand, the collapse became inevitable and irreversible. As the protosolar nebula contracted under its own weight, basic physics transformed this cold gas cloud. It became an increasingly hot and dense sphere. Gravitational potential energy converted to thermal energy. It heated the collapsing material from nearly absolute zero to thousands of degrees. The cloud began spinning faster as it shrank, following the same principle that makes ice skaters spin faster when they pull in their arms. This rotation flattened the nebula into a disk with a dense central bulge. That would eventually become our sun. The collapse accelerated dramatically once it began. What started as a process taking millions of years compressed into rapid contraction. The final phase lasted just 100,000 years. The central temperature climbed steadily. 1,000 degrees, 10,000 degrees, 100,000 degrees. When the core finally reached 10 million degrees Celsius, hydrogen nuclei began fusing together for the first time. Nuclear fusion ignited like a cosmic match strike. Our sun announced its birth with the first steady glow of stellar fire. This stellar delivery wasn't a gentle emergence. The newborn sun experienced violent growing pains called the T-Tauri phase. It was characterized by powerful stellar winds that blew away leftover gas and dust from the surrounding disk. These infant stellar tantrums were thousands of times more energetic than anything our mature sun produces today. The young star flickered and flared unpredictably as it struggled to establish stable nuclear burning in its core. Within the first 50 million years, gravitational collapse had transformed a cold, dark gas cloud into a blazing nuclear furnace that has been burning steadily ever since. The leftover disk material eventually condensed into planets, asteroids, and comets, including Earth and everything on it. Every atom in your body was forged either during this stellar birth process or in the cores of previous generation stars. They lived and died before our sun even existed. We are literally made of star stuff. We are children of a cosmic delivery room that operated 4.6 billion years ago. Our sun has reached what astronomers call stellar middle age. It is the stable, productive phase of stellar life where nuclear fusion burns hydrogen into helium with remarkable consistency. For the past 4.6 billion years, our neighborhood star has maintained this steady state. It plans to continue this reliable performance for another 5 billion years. This represents the main sequence phase, when stars spend roughly 90% of their entire lifetimes as stable hydrogen-burning furnaces. Think of the sun as a cosmic civil servant who's been showing up to work every day for 4.6 billion years. Without calling in sick, taking vacation, or demanding a raise. This stellar reliability results from an elegant balance between two opposing forces. Gravitational collapse tries to crush the sun inward. Nuclear fusion pressure pushes outward. These forces have remained in nearly perfect equilibrium for billions of years, creating the stable energy output that makes life possible on Earth. During this main sequence phase, the sun operates like the universe's most efficient office worker. Every second, it processes 600 million tons of hydrogen fuel through nuclear fusion. It converts 4 million tons of matter into pure energy. It maintains remarkably consistent output. The fusion reactions occur exclusively in the central 25% of the solar interior, where temperatures and pressures remain high enough to overcome the electrical repulsion between hydrogen nuclei. This stellar middle age brings gradual changes that occur so slowly they're barely detectable across human timescales. The sun grows approximately 10% brighter every billion years as helium ash accumulates in its core, making the central region denser and slightly hotter. This subtle brightening has been ongoing throughout Earth's history. Yet our planet has somehow maintained liquid oceans despite receiving gradually increasing solar energy. Complex feedback mechanisms in Earth's climate system have compensated for this slow stellar evolution. Astronomers can study the sun's main sequence phase by observing similar stars at various stages of hydrogen burning throughout our galaxy. Stars with masses similar to our sun follow predictable evolutionary tracks, burning hydrogen for roughly 10 billion years before exhausting their core fuel supplies. More massive stars burn through their hydrogen much faster, completing their main sequence phase in just millions of years. Smaller red dwarf stars burn so slowly they can remain on the main sequence for trillions of years. What makes our sun's main sequence longevity particularly remarkable is its stability. It has enabled the gradual development of complex life on Earth. Biological evolution requires stable environmental conditions maintained across deep time. If our sun were more massive, it would have already evolved off the main sequence and destroyed Earth's biosphere. If it were less massive, Earth might still be a frozen world waiting for complex chemistry to begin. The sun's mass falls within the narrow range that provides both sufficient energy for life and the long-term stability needed for evolution to produce intelligent observers. 5 billion years from now, our well-behaved sun will experience the stellar equivalent of a midlife crisis, one that makes any human midlife crisis look like a minor mood swing. When hydrogen fuel in the solar core finally runs out, our star will abandon its 10 billion year career as a stable main sequence star. It will transform into a red giant, a bloated, unstable stellar monster that will expand to swallow Mercury, Venus, and possibly Earth itself. This dramatic transformation begins when the sun exhausts hydrogen in its central core after 10 billion years of steady nuclear burning. With no more fusion fuel to generate the outward pressure needed to balance gravitational collapse, the core begins contracting under its own weight. But here's where stellar physics becomes counterintuitive. As the core shrinks and heats up, hydrogen fusion actually becomes more vigorous in a shell surrounding the depleted core. This shell burning produces more energy than the sun generates today. But the extra energy goes into inflating the outer layers of the star rather than increasing surface brightness. The sun's outer atmosphere begins expanding like a cosmic balloon. growing larger and cooler as it stretches across millions of kilometers of space. During peak red giant phase, our Sun will expand to roughly 200 times its current diameter, large enough that its surface would reach nearly to Earth's current orbital distance. The red giant Sun will become a stellar lightweight champion. It will contain the same mass as today, but spread across a volume millions of times larger. This makes the outer layers incredibly tenuous, essentially a hot vacuum by earthly standards. Yet these gossamer outer regions will glow with brilliant red light, making the red giant Sun thousands of times more luminous than our current star despite its cooler surface temperature. This inflated stellar atmosphere will be gravitationally unstable, pulsating and shedding mass into space like cosmic breathing. Strong stellar winds will carry away significant portions of the Sun's outer layers, gradually reducing the star's total mass. These winds will create spectacular nebulae as ejected material interacts with ultraviolet radiation from the hot central core. The dying Sun will essentially turn itself inside out. It will expose its nuclear burning interior while dispersing its atmosphere across light years of space. From Earth's perspective, assuming our planet somehow survives, the red giant Sun will dominate the sky. It will look like a vast crimson disk, hundreds of times larger than today's Sun. Surface temperatures on Earth will soar to over 1,000 degrees Celsius, boiling away the oceans and atmosphere. Even if Earth's orbit expands due to the Sun's decreasing mass, our planet will likely be engulfed by the extended solar atmosphere. The stable, life-supporting relationship between Earth and Sun will end in a spectacular stellar funeral pyre. It will transform our solar system beyond recognition. After spending millions of years as a bloated red giant, our dying Sun will perform one final act of cosmic theater. It will be a spectacular striptease that gradually sheds its outer layers into space while revealing the hot, dense stellar core beneath. This process will transform our massive star into a white dwarf, a stellar remnant about the size of Earth. It will contain roughly half the Sun's original mass compressed into a sphere smaller than most planets. The transformation begins during the red giant's most unstable phase, when the Sun's outer atmosphere becomes so distended that even weak stellar winds can carry away significant amounts of material. These mass loss episodes intensify over time, accelerating from gentle breezes to powerful stellar hurricanes that strip away the star's outer layers like cosmic erosion. Eventually, the Sun will lose nearly half its total mass to these stellar winds, dispersing its atmosphere across the interstellar medium. As the outer layers dissipate, they reveal the Sun's core, a white-hot sphere of carbon and oxygen compressed to incredible densities. This stellar remnant, called a white dwarf, packs roughly 0.6 solar masses into a volume smaller than Earth. A teaspoon of white dwarf material would weigh about 5 tons on Earth. It demonstrates the extreme density achieved when stellar core collapse is finally halted by quantum mechanical pressure rather than nuclear fusion. The newly exposed white dwarf initially blazes at temperatures exceeding 100,000 degrees Celsius, nearly 20 times hotter than our current Sun's surface. Despite its small size, this intense heat makes the white dwarf extremely luminous in ultraviolet light. The surrounding expelled material glows brilliantly when illuminated by this central furnace. It creates what astronomers call a planetary nebula, one of the universe's most beautiful stellar death displays. These planetary nebulae have nothing to do with planets despite their name. Early telescopes revealed them as disk-shaped objects resembling planetary images, but they actually represent the illuminated funeral shrouds of dying stars. The Ring Nebula, Cat's Eye Nebula, and other spectacular examples show us preview images of our sun's eventual fate. They are glowing shells of ejected, stellar material surrounding tiny white dwarf cores. The white dwarf phase represents stellar retirement rather than stellar death. With no nuclear fuel remaining, the white dwarf cannot generate new energy through fusion. Instead, it slowly radiates away the thermal energy stored during its formation, gradually cooling from white-hot to yellow, then red, and eventually becoming too dim to see. This cooling process occurs incredibly slowly. A white dwarf takes billions of years to fade significantly. Our sun's white dwarf remnant will continue glowing long after the current universe grows cold and dark. The final chapter of our sun's biography will be written not in fire and fury, but in the slow, inexorable cooling of a stellar ghost. After the dramatic planetary nebula phase ends and the expelled material disperses into interstellar space, the white dwarf remnant begins an epic journey toward absolute zero. That will span hundreds of billions of years, longer than the current universe has existed. This cooling process follows the relentless laws of thermodynamics. With no nuclear fusion to generate new heat, the white dwarf can only radiate away the thermal energy stored in its crystalline interior. The surface temperature drops steadily from 100,000 degrees to 50,000 degrees. Then 10,000 degrees as millennia pass like cosmic heartbeats. The white dwarf's color gradually shifts from blazing blue-white to yellow, then red, then infrared as it slowly fades from view. What makes this stellar death particularly poignant is the incredible time scales involved. A white dwarf requires approximately 10 billion years just to cool from 100,000 degrees to 5,000 degrees, roughly the same time span as our sun's entire main sequence lifetime. During the next 100 billion years, it will continue cooling toward 3,000 degrees. The final approach to absolute zero could take trillions upon trillions of years, extending far beyond any meaningful concept of cosmic time. Eventually, our sun's white dwarf will become what astronomers call a black dwarf, a cold, dark stellar corpse that no longer emits detectable light. This represents true stellar death, when a once mighty star finally exhausts all its thermal energy and reaches equilibrium with the cosmic background temperature. Black dwarfs will be among the last objects remaining in a universe that has expanded and cooled to near absolute zero. The universe hasn't existed long enough for any white dwarfs to complete this cooling journey to black dwarf status. Current white dwarf observations show stellar remnants at various stages of the cooling process. But even the oldest white dwarfs in our galaxies still glow with residual heat from their formation billions of years ago. Our sun's eventual black dwarf phase remains purely theoretical, a distant stellar future that exceeds the current age of the universe by factors of millions. This ultimate fate provides humbling perspective on stellar longevity. Our sun will spend roughly 10 billion years as an active hydrogen-burning star. It will then spend perhaps 100 million years transitioning through red giant and planetary nebula phases. But it will spend hundreds of billions of years cooling as a white dwarf, and potentially trillions of years as a cold black dwarf. The vast majority of our sun's existence will occur as a slowly cooling stellar remnant, gradually fading toward cosmic invisibility while the universe expands and evolves around its ghost. In the end, our sun will become a monument to stellar mortality, a planet-sized diamond floating through the cosmic dark, carrying within its crystalline structure the compressed remains of billions of years of nuclear fusion. This stellar gravestone will persist long after galaxies merge, stars burn out, and black holes evaporate through Hawking radiation. The Sun's final gift to the cosmos will be its nearly eternal preservation of the matter that once powered our solar system, locked in a crystalline time capsule that could survive until the heat death of the universe itself. Long before anyone understood nuclear fusion or stellar evolution, ancient humans looked up at the blazing disk crossing their skies. They made a reasonable assumption. This must be a god. The sun's daily journey from east to west seemed like clear evidence of divine power. So did its seasonal changes in height and intensity. So did its obvious control over life and death on Earth. Yet these same ancient sun worshippers accidentally invented astronomy while trying to honor their celestial deity. Every major civilization developed elaborate myths around solar worship. The Egyptians believed Ra sailed across the sky in a golden boat, battling darkness each night to ensure sunrise the next day. Greeks imagined Helios driving a chariot pulled by fire-breathing horses. Aztecs fed human hearts to Huitzilopochtli to guarantee the sun would rise again. These weren't primitive superstitions. They represented humanity's first serious attempts to understand the most important object in their universe. But religious devotion led to scientific observation almost by accident. Egyptian priests needed to predict when the Nile would flood, so they carefully tracked the sun's position relative to stars throughout the year. Mayan astronomers developed incredibly precise calendars by measuring subtle changes in solar angles across seasons. Stonehenge and dozens of similar monuments served as massive solar calculators, marking solstices and equinoxes with architectural precision that rivals modern instruments. These ancient solar observations produced surprisingly accurate results. The Maya calculated the year length as 365.2420 days. It was just 0.0002 days off from our modern measurement. Egyptian astronomers determined that seasonal patterns repeated every 365.25 days. This led them to invent leap years over 4,000 years ago. Chinese astronomers recorded detailed sunspot observations during periods when atmospheric haze made direct solar viewing possible, creating the world's first systematic solar activity records. What makes ancient solar astronomy particularly remarkable is how these civilizations achieved precision without understanding what they were actually observing. They didn't know the sun was a star, or that Earth orbited around it, or that seasonal changes resulted from planetary tilt. Yet they successfully predicted eclipses, tracked solar cycles, and created calendars accurate enough to organize entire agricultural societies. They treated the sun as a divine timekeeper and accidentally discovered that this celestial god followed remarkably predictable mathematical laws. These ancient solar calendars became the foundation for organized civilization. Agriculture required precise timing for planting and harvesting. Religious festivals needed scheduling around seasonal celebrations. Administrative systems depended on standardized time measurements. The sun's apparent motion provided the cosmic clockwork that synchronized human society. It transformed nomadic tribes into settled civilizations that could plan decades into the future. Ancient sun worship created the world's first science project, one that is still running today in the form of our modern calendar system. For over 1,000 years, scholars accepted Aristotle's teaching that celestial objects were perfect, unchanging spheres. They were made of pure crystalline material. The sun, being the most important celestial body, was assumed to be absolutely flawless, a divine disk of pure light unmarred by any imperfections. This comfortable assumption about solar perfection would be spectacularly destroyed in 1610. Galileo Galilei pointed a primitive telescope at the sun. He discovered something that should not exist. Dark spots were scattered across its surface. Galileo's solar observations required considerable courage and ingenuity. Looking directly at the sun through any optical instrument should instantly blind the observer. Instead, Galileo projected the sun's image onto screens and used smoked glass filters to safely study solar details. What he saw through his crude 20-power telescope revolutionized humanity's understanding of our local star. The supposedly perfect solar disk was covered with dark blemishes. They appeared, moved, and disappeared over periods of days and weeks. These sunspot observations provided the first direct evidence that the sun rotated on its axis. Galileo tracked individual spots as they moved across the solar disk from east to west. It took about 14 days to cross the visible face of the sun. This meant the sun must be spinning with a rotation period of roughly 28 days. This made it a dynamic, moving object rather than a fixed celestial ornament. The perfect heavens were actually full of spinning, changing, spotted celestial bodies. They behaved more like planets than divine decorations. The religious and scientific establishment initially rejected Galileo's sunspot discoveries. Jesuit astronomers argued that the spots must be small planets orbiting close to the sun. This preserved the fiction of solar perfection. Others claimed the spots were optical illusions created by imperfect telescopes. The idea that celestial objects could have surface features and temporary blemishes challenged fundamental assumptions about the nature of heaven and divine creation. Galileo's sunspot studies also revealed that these features weren't randomly scattered across the solar surface. Spots appeared most frequently in two bands north and south of the solar equator. They rarely appeared near the poles or directly on the equatorial line. They seemed to follow patterns and cycles. Sometimes they appeared in large groups. Other times they remained absent for weeks at a time. The sun wasn't just imperfect, it was demonstrably active and variable. This discovery marked the beginning of modern solar astronomy. Once astronomers accepted that the sun had a real surface with observable features, they could begin studying how our star actually worked. They no longer had to simply calculate its position in the sky. The perfect, unchanging celestial sphere of ancient philosophy was replaced by a dynamic, spotted, rotating ball of fire. It displayed measurable patterns of activity. Galileo's telescope had transformed the sun from a divine symbol into a scientific object worthy of detailed study. In the 1800s, scientists developed a revolutionary new tool that could analyze light itself like a cosmic fingerprint scanner. Spectroscopy allowed astronomers to determine the chemical composition of distant objects without ever touching them. When they pointed these rainbow-analyzing instruments at the sun, they made a discovery that seemed impossible. Our star contained an element that didn't exist anywhere on Earth. The spectroscopic revolution began when Joseph von Fraunhofer discovered that sunlight wasn't actually pure white when examined closely. Passing solar radiation through a prism revealed thousands of dark lines scattered across the rainbow spectrum, like a cosmic barcode. These absorption lines occurred where specific chemical elements in the sun's atmosphere absorb particular wavelengths of light. Each element created its own unique pattern of spectral lines. This gave astronomers a way to identify stellar chemistry from 150 million kilometers away. Scientists soon recognized familiar patterns in the solar spectrum. Iron, calcium, magnesium, sodium, and hydrogen all left their characteristic fingerprints in sunlight. This confirmed that the Sun contained many of the same elements found on Earth. This provided the first direct evidence that celestial objects were made of ordinary matter. They were governed by the same physical laws as terrestrial materials. The heavens weren't constructed from mysterious celestial substances. They were built from the same atomic building blocks as everything on our planet. But in 1868, French astronomer Jules Janssen and British astronomer Norman Lockyer independently discovered something extraordinary during a solar eclipse. They detected a bright yellow emission line in the solar spectrum that didn't match any known element. This mysterious spectral signature appeared consistently in solar observations but couldn't be reproduced in any earthly laboratory. They had found conclusive evidence for an element that existed in the Sun but nowhere on Earth. Lockyer named this unknown element helium after Helios, the Greek sun god, since it seemed to be exclusively a solar material. For nearly 30 years, helium remained a theoretical element known only from solar spectroscopy. Chemists couldn't isolate it, couldn't create it artificially, and couldn't find it in any terrestrial minerals. The Sun apparently contained a type of matter that didn't exist on our planet, a cosmic element that defied earthly chemistry. The mystery was finally solved in 1895 when Scottish chemist William Ramsay discovered helium gas trapped in radioactive uranium ore on Earth. This confirmed that the spectroscopic detectives had correctly identified a real element nearly 3 decades before anyone could study it in terrestrial laboratories. The Sun had revealed one of its secrets through the language of light. It taught humanity about the existence of helium before we could find it in our own world. This triumph demonstrated the incredible power of spectroscopic analysis and established our star as humanity's first extraterrestrial chemistry laboratory. For most of human history, we could only see the Sun's visible light personality, the familiar yellow-white disk that illuminates our daytime sky. Earth's atmosphere acts like a cosmic filter that blocks most of the electromagnetic spectrum. It hides the Sun's true multi-wavelength character from ground-based observers. Only when we finally escaped our planetary atmosphere with rockets and satellites did we discover something. Our seemingly familiar star has been hiding an incredibly violent and dynamic invisible personality. The first space-based solar telescopes revealed a completely different Sun operating in ultraviolet and X-ray wavelengths. Instead of the smooth, relatively calm surface visible to human eyes, these new instruments showed a star in constant turmoil. Magnetic field lines twisted and snapped with explosive violence. Plasma streams raced along invisible magnetic highways at thousands of kilometers per second. The solar corona blazed with X-ray emissions from plasma heated to millions of degrees, temperatures that had no right to exist in the Sun's outer atmosphere. NASA's Solar and Heliospheric Observatory, launched in 1996, positioned itself 1.5 million kilometers from Earth. It sat at the L1 Lagrange point. This is a gravitational balance point that provides uninterrupted views of the Sun. It avoids Earth's atmospheric interference. SOCHO's instruments could observe solar activity across multiple wavelengths simultaneously. They revealed how energy and material flow through different layers of the solar atmosphere with unprecedented detail. These space-based observations solved decades-old mysteries while creating entirely new puzzles. astronomers finally understood how coronal mass ejections form and propagate through the solar system. They could track the 11-year solar cycle's magnetic field reversals in real time. They discovered that the quiet sun actually experiences thousands of tiny explosions called nanoflares. They constantly heat the corona through magnetic reconnection, events too small to detect from Earth. But space-based solar astronomy also revealed how much we still don't understand about our nearest star. The coronal heating problem remains unsolved despite decades of high-resolution space observations. We still do not know why the sun's outer atmosphere is hundreds of times hotter than its surface. The precise mechanisms driving solar flares and coronal mass ejections are still being debated. Even basic questions about how the solar magnetic field generates and reverses its polarity every 11 years lack complete answers. The Parker Solar Probe, launched in 2018, represents the ultimate expression of space-age solar science. This spacecraft is flying closer to the Sun than any previous mission, eventually reaching within 7 million kilometers of the solar surface, close enough to actually sample particles from the corona itself. Protected by a revolutionary heat shield, Parker can withstand temperatures exceeding 1400 degrees Celsius. It is providing the first direct measurements from within the solar atmosphere. Modern solar astronomy has transformed our understanding of stellar physics while revealing how much more we have to learn. Ground-based observations showed us a predictable, relatively static star. Space-based instruments revealed a dynamic, violent, magnetically active plasma furnace. It constantly reshapes the space environment throughout our entire solar system. The sun we thought we knew from centuries of earthbound observation represents only a tiny fraction of our star's true electromagnetic personality, a cosmic revelation that required escaping our own planet's atmosphere to fully appreciate. While humanity worries about climate change over decades and centuries, our sun is quietly executing a much longer-term plan, one that will eventually transform Earth into a lifeless desert world. Over each billion years, our neighborhood star grows roughly 10% brighter. As helium ash accumulates in its core, it gradually intensifies the solar radiation that reaches our planet. This stellar brightening occurs so slowly that 1,000 human generations might pass without noticing any change. Yet it represents an unstoppable countdown toward the complete evaporation of Earth's oceans. This solar evolution follows the inexorable physics of stellar aging. As the sun converts hydrogen into helium through nuclear fusion, the helium byproducts settle into the stellar core like cosmic sediment. This helium ash is denser than hydrogen. It makes the core slightly more compact, and it raises the central temperature. Higher core temperatures accelerate fusion reactions. They cause the sun to produce more energy and radiate more intensely toward Earth. The brightening rate seems almost negligible on human timescales, roughly 10% per billion years. Yet this gradual change will eventually trigger catastrophic consequences for Earth's climate system. Computer models predict that within 1 billion years, increased solar radiation will heat Earth's surface enough to cause runaway water vapor feedback. As oceans warm and evaporate faster, the additional water vapor in the atmosphere will trap even more heat. This accelerates the warming process until all liquid water disappears from the planet's surface. This represents a cosmic deadline that no amount of human technology or climate engineering can ultimately prevent. Earth's oceans have survived ice ages, asteroid impacts, massive volcanic eruptions, and dramatic changes in atmospheric composition. but they cannot survive the sun's inevitable stellar evolution. Within 1 billion years, Earth will experience its final sunrise over liquid water. That is roughly 200 times longer than complex life has existed on our planet, before it transforms into a Venus-like greenhouse world. The timeline provides both comfort and urgency for humanity's long-term survival. 1 billion years exceeds any meaningful human planning horizon by factors of millions. Our entire species has existed for only 300,000 years, while recorded civilization spans merely 5,000 years. A billion-year future gives humanity ample time to develop interstellar travel, terraform other worlds, or discover entirely new approaches to cosmic survival that we can't currently imagine. Yet this distant solar deadline also highlights the fundamental impermanence of Earth's habitability. Our planet's ability to support life isn't a permanent cosmic guarantee. It's a temporary phase in stellar evolution that happens to coincide with our current existence. The sun that makes life possible today will eventually become so bright that it destroys the very biosphere it once nurtured. This cosmic irony reminds us that even our most essential celestial relationships are ultimately temporary arrangements in the vast timescales of stellar evolution. Every few decades, our sun experiences stellar mood swings so violent they can cripple human technology across an entire hemisphere. This can happen within minutes of eruption. These solar storms involving coronal mass ejections and extreme solar flares represent a clear and present danger to our increasingly electronic civilization. Unlike the gradual billion-year brightening that threatens Earth's distant future, solar storms pose immediate risks to satellites, power grids, and communication systems. These are systems that modern society depends on for basic functions. The threat became starkly apparent during the Carrington event of 1859, when the most powerful solar storm in recorded history caused telegraph systems worldwide to malfunction spectacularly. Telegraph operators received electric shocks from their equipment. Telegraph lines sparked and ignited fires in multiple cities. Some telegraph systems continued operating without their power supplies. They drew electricity directly from geomagnetic disturbances caused by solar particles interacting with Earth's magnetosphere. Modern civilization's vulnerability to solar storms exceeds anything our ancestors faced during the telegraph era. Today's power grids rely on high-voltage transmission lines spanning thousands of kilometers. They are perfect antennas for capturing electrical currents induced by geomagnetic disturbances. GPS satellites, internet infrastructure, financial networks, and air traffic control systems all depend on electronics. Intense solar radiation can damage or disrupt them. Charged particle bombardment can do the same. A Carrington-level event occurring today could cause catastrophic cascade failures across interconnected technological systems. Electrical transformers might overload and burn out. This could cause regional blackouts lasting weeks or months while replacement equipment is manufactured and installed. Satellite navigation systems could provide inaccurate positioning data. This could disrupt everything from shipping routes to precision agriculture. Radio communications might become unreliable just when emergency coordination becomes most critical. The economic consequences of extreme solar weather could exceed those of major hurricanes or earthquakes. In 2008, the National Academy of Sciences estimated the first year could bring $1 to $2 trillion in damages. Full recovery could require 4 to 10 years. Unlike terrestrial natural disasters that affect limited geographic regions, solar storms can impact entire continents simultaneously. They can overwhelm traditional disaster response capabilities. Space weather forecasting has emerged as a critical component of national security and economic planning. Organizations like NOAA's Space Weather Prediction Center monitor solar activity continuously. They provide advance warnings when dangerous solar storms head toward Earth. Satellite operators can temporarily shut down sensitive electronics. Airlines reroute flights away from polar regions where radiation exposure increases. Power companies can reduce electrical loads on vulnerable transmission lines. Yet our best space weather predictions currently provide only 15 to 60 minutes of advance warning for the most dangerous types of solar storms. This brief lead time forces modern civilization to live with perpetual vulnerability to solar tantrums. That could disrupt everything from bank transactions to hospital life support systems. The sun's unpredictable moods remind us that our technological civilization exists at the mercy of stellar physics we still don't fully understand or control. Every hour, the sun delivers more energy to Earth's upper atmosphere than human civilization consumes in an entire year. This cosmic power plant operates continuously without fuel costs, maintenance schedules, or carbon emissions. It provides thousands of times more energy than humanity could ever need. Solar technology has finally matured to the point where it can capture meaningful fractions of this stellar bounty. It offers the tantalizing possibility of virtually unlimited clean energy for as long as our sun continues burning. The transformation of solar technology over recent decades resembles the evolution of computers. From expensive, inefficient novelties to ubiquitous, essential infrastructure, early solar panels achieved efficiencies around 6% while costing hundreds of dollars per watt. Modern photovoltaic cells routinely exceed 20% efficiency. Laboratory demonstrations have reached over 40%. Meanwhile, manufacturing costs have plummeted by more than 95% since 1980. This has made solar electricity cheaper than fossil fuels in many regions. This solar revolution has accelerated so rapidly that even optimistic projections from just 2 decades ago underestimated the actual deployment rates. Global solar capacity has doubled roughly every 3 years since 2000. It has reached over 1,000 gigawatts installed worldwide, enough to power major industrialized nations. Countries like Germany and California now generate more than half their electricity from renewable sources during peak solar production hours. This demonstrates the practical viability of solar-powered civilizations. The ultimate potential for solar energy harvesting defies easy comprehension. Covering just 0.3% of Earth's land surface, with modern solar panels would generate enough electricity to meet current global energy demands. Deploying solar installations across suitable desert regions could theoretically power human civilization at current consumption levels for millions of years. This is limited only by the sun's remaining hydrogen fuel supply, rather than terrestrial resource constraints. Advanced solar concepts could capture even larger fractions of stellar energy through space-based installations or orbital solar power satellites. These systems would collect sunlight above Earth's atmosphere. They would avoid weather and day-night cycles, while achieving higher efficiencies than ground-based panels. Microwave power transmission could beam energy from orbital collectors to receivers anywhere on Earth's surface. It could provide continuous solar power even during local nighttime hours. The environmental implications of large-scale solar adoption could help address climate change while reducing humanity's dependence on finite fossil fuel resources. Solar installations produce no greenhouse gas emissions during operation. They require no water for cooling. They generate no radioactive waste or air pollution. Unlike wind power that depends on weather patterns or hydroelectric dams that alter river ecosystems, solar panels work anywhere the sun shines. They work without disrupting natural environmental processes. Yet challenges remain in transitioning to a truly solar-powered civilization. Energy storage technologies must improve to provide reliable power during cloudy periods and nighttime hours. Electrical grid infrastructure requires upgrades to handle variable renewable energy sources. Manufacturing sufficient solar panels to replace fossil fuels will require massive industrial expansion and raw material extraction. Nevertheless, the fundamental physics of solar energy harvesting offers humanity a clear pathway toward sustainable energy abundance. It is powered directly by our neighborhood star. For over 70 years, scientists have pursued humanity's most audacious energy project. They aim to recreate the sun's nuclear fusion process in earthly laboratories, to provide unlimited clean power. This quest to build artificial stars represents the ultimate attempt to harness stellar physics for human benefit. It promises energy so abundant and clean that it could solve global warming and eliminate energy poverty. It could power human expansion throughout the solar system for millions of years. The basic fusion fuel cycle mirrors what happens inside the sun's core, but it uses isotopes of hydrogen that are easier to fuse under laboratory conditions. Deuterium and tritium can undergo fusion reactions at only 100 million degrees Celsius. This is compared to the 15 million degrees required for ordinary hydrogen fusion. When these heavy hydrogen nuclei combine, they produce helium plus high-energy neutrons. These neutrons carry away the fusion energy for conversion to electricity. Current fusion research follows two primary approaches that attempt to replicate stellar conditions through different methods. Magnetic confinement fusion uses powerful magnetic fields to contain superheated plasma in donut-shaped chambers called tokamaks. Inertial confinement fusion blasts tiny fuel pellets with intense laser beams. It compresses hydrogen to stellar densities for brief moments. Both techniques have achieved genuine fusion reactions, but neither has yet produced more energy than it consumes. The engineering challenges of controlled fusion exceed almost any previous human technological undertaking. Plasma at 100 million degrees cannot touch any material container. This requires magnetic bottles or precisely timed compression to prevent the fusion fuel from cooling and escaping. The extreme temperatures and radiation levels create materials science problems that push technology far beyond current capabilities. Success requires simultaneously mastering plasma physics, superconducting magnets, high-energy lasers, and radiation-resistant materials. Recent breakthrough experiments have brought practical fusion power closer to reality than ever before. In December 2022, scientists at the National Ignition Facility achieved fusion ignition. This produced more energy from fusion reactions than the laser energy delivered to the fuel pellet. This milestone proved that net energy gain from controlled fusion is physically possible. Scaling up to practical power generation will still require decades of additional development. The potential rewards of successful fusion development could transform human civilization. Fusion fuel is essentially inexhaustible. Deuterium can be extracted from seawater, while tritium can be produced from lithium using neutrons from the fusion reaction itself. The fusion fuel in 1 gallon of seawater contains energy equivalent to 300 gallons of gasoline. A fusion power plant would produce no greenhouse gases, no long-lived radioactive waste, and no possibility of meltdown accidents. Private companies now complement government fusion research programs with novel approaches that promise faster development timelines. Companies like Commonwealth Fusion Systems, Tide Technologies, and Helium Energy claim they can demonstrate practical fusion power within the next 10 to 15 years. They aim to do this using advanced superconducting magnets, alternative reactor designs, and improved plasma control systems. Whether these optimistic projections prove realistic, the global fusion research effort represents humanity's most ambitious attempt to capture stellar power for earthly use. If successful, controlled fusion could provide the ultimate energy source for human expansion beyond Earth. Fusion-powered spacecraft could travel throughout the solar system using fuel extracted from water on any planet or moon. Space colonies could operate fusion reactors using materials available throughout the cosmos. Mars terraforming projects could be powered by fusion plants that require no imported fuel from Earth. The same stellar physics has powered our Sun for 4.6 billion years. It could eventually enable human civilization to flourish across the galaxy. It would carry the gift of controlled stellar fire to any world where we choose to make our home.